I want to start by stepping back and asking this question, why is it that we're in this position in the first place of having such an incredibly successful theory that we have no good metaphysical or philosophical understanding of? So how is it that we ended up in this situation? And I think one way of getting an understanding of this is actually looking back at physics as a kind of organism which has lived for something like 400 years. And it obviously, we start with classical mechanics as the foundation point, electrodynamics, the theories of relativity, and then quantum mechanics. And then I've missed out a whole load of things after that, but perhaps not a huge amount happens in a fundamental sense, except perhaps quantum field theory and quantum electrodynamics, but that's still built within this quantum theoretic framework. And over the course of time, we see enormously growing power. There's this interplay with technology, which was discussed very nicely yesterday. And there's also this incredible interplay with society in the sense that as physics confers great economic and military advantage to societies, they adopt science, they adopt physics, they institutionalize it, and that changes the character of physics and science itself. It becomes more utilitarian. So there's a big story here. There's many layers of this story. But I want to focus in on something very specific, namely the relationship between physics and metaphysics in particular. It starts off, physics starts off at the outset as natural philosophy rather than physics. So it's got this extremely close connection to metaphysics. And the metaphysical foundations for classical mechanics in particular were consciously staked out by the founders of classical mechanics, Descartes, Newton, Leibniz, and many other relatively minor figures, but they all played a critical role in fleshing out a geometrical, mechanical, atomistic conception of reality. And that conception is based fundamentally on a partitioning of reality, space-time, matter, laws, observation, and one could add agency to this. And then theoretical assumptions are made within these specific categories, driven by desiderata like mathematizability and universality. And so we have, for example, the idea of space being continuous, homogeneous. Isotropics are all places, all directions are treated on an equal footing. All times are treated on an equal footing. And so what we have then right at the outset is a very uniform, maximally symmetric canvas on which everything happens that becomes very mathematizable. So this is in sharp contrast to, say, the Aristotelian perspective, right, which would privilege, it would privilege time, it would privilege location as well. And then matter, there's a very interesting debate in the 17th century between the actual parts doctrine and the potential parts doctrine, which I'll come back to later. And so the actual parts doctrine really licensed the idea that every composite body can be viewed as simply an arrangement of actually existing parts. And then atomism adds this extra layer that there are some fundamental elements out of which everything is built. And then these parts are regarded as indefinitely persistent. And then we have primary, secondary quality distinction. And then we have a distinction between static properties and dynamic properties. So all of these sort of positions were staked out. And because of this picture of matter, all objects are treated uniformly, whether they're thinking beings or living beings or inanimate beings. It doesn't matter where they are. So again, this is fitting into this idea of a universal framework, which doesn't privilege any kind of object over any other kind of object. And then we have laws that are unchanging. They're not material, they're unchanging, and yet they have causal efficacy. They're deterministic, they're reversible. And then we have a compositional property that's sort of built into the laws, which mean that we can scale up our knowledge. So if we understand how, say, in the Newtonian framework, just two particles interact, then we can scale that up to any number of particles effortlessly through the parallelogram of forces. And that's crucial, again, if we want to mathematize laws in such a way that has universal applicability. And then finally, observation is treated in this very extreme extrapolation from everyday visual experience. It's assumed to be perfectly passive and at the same time as exact, right? So it basically, it's modeled after our visual sense rather than our tactile sense. And what this really means is that observation does not need to appear in the postulates of classical theories. It can appear as the background assumptions of the theory. And then as I said, agency I didn't mention, but the whole framework presupposes that human agency can be partitioned off somehow, and somehow that which originates or causal chains can be ignored for the most part, and it leaves open exactly where that boundary is. So there's a big conception here underlying classical physics, and this is really what I'm talking about when I talk about the classical conception of reality. And that really sustained physics for something like 250 years. And we have the classical mathematical framework, which is this abstract framework of states, deterministic reversible evolution, and measurements that simply can read off the state. That's all built into this. And then specific classical physical theories like Newtonian mechanics are built within it by adding additional postulates of a more physical nature, like the principle of relativity. And I think it's this sort of majestic tripartite structure which gives us the sense of understanding classical physics, right? So we're going all the way from a consciously staked out metaphysical foundation all the way to mathematical detailed theories. And then we have a clear linkage to experiment. And I want to emphasize that the understandability is there despite the fact that the classical conception conflicts with many aspects of lived experience. And there's a kind of trade-off going on here. We're trading off immediate concordance with lived experience for things like symmetry, universality, and mathematizability. And to some extent, we're able to recover contingently everyday experience. For example, the asymmetry of up and down, we can understand that in the Newtonian framework as a contingent fact that we're living on the Earth. But notions like the wholeness of organisms or free will, those are not something that one can simply recover in any fundamental way within this framework. So going back to this picture then, we've got classical mechanics on the one hand, which is built in this very deliberate way on a clearly staked out metaphysical foundation. But what happens over time is that for a variety of reasons, both internal and sort of external reasons, physics becomes so much more autonomous. It gains the capacity, it realizes it has the capacity to develop new physical theories without consciously engaging, like in a very deliberate way, with metaphysics. Catherine Brading has this wonderful phrase that at some point, physics flew the philosopher's nest. So at some point, these disciplines kind of pulled apart, and you can date it roughly, I think, to after Principia, right? So like early 18th century, I think you can date it. And as a result of this increasing autonomy, we have physical theories being developed, like, first of all, Maxwell's equations, which are successful, incredibly successful, but are more driven by the experimental phenomena of interest. And then it's not clear what they metaphysically mean. Yes?
Sorry to Phil, but isn't maybe one reason potentially there's something that's missing right from the middle there thermodynamics.
Yes, I didn't. I kind of left that uncluttered. There's lots here. There's thermodynamics, there's optics, there's early electricity and magnetism. Yeah.
Specifically, as an example of a suggested theory without clear metaphysical underpinning is something leading to this. Thermodynamics seems.
I think that's a great point. Yes. So thermodynamics is a great example of a non-fundamental theory, right? Where it's got very clear postulates, where the heat death discussion comes up. Absolutely. So I'm focusing here on, you could say, the fundamental theories, but absolutely. And so we have theories starting here with Maxwell's equations, Maxwell's theory, where it's not terribly clear how to interpret it. And so this is actually the first example I just want to look at of the problem of interpretation of these theories. So obviously, Maxwell's equations are based on Faraday's field conception. So a mathematical clothing, if you like, of Faraday's field conception. And the prediction of electromagnetic waves then was naturally understood as implying a medium, right? So this was the movement from the notion of electromagnetic waves to the notion of a medium. And so for around 40 years, between 1865 and 1905, you've got Maxwell's theory is interpreted almost universally with respect to an ether frame. And accommodation was made to deal with the null results of Michelson-Morley by ad hoc devices like Fitzgerald contraction, which was then generalized to the Lorentz transformations that were identified by Lorentz and Poincaré. But still, Maxwell's equations were interpreted relative to the ether frame. And it wasn't until then, 1905, where Einstein isolated this mathematical feature of the Lorentz theory that was not well understood, physically well understood, and actually showed that they had deep meaning by deriving them completely separated from Maxwell's theory, that it became clear that this ether concept was not really an appropriate way of thinking about Maxwell's theory. And in fact, then you have these extraordinary consequence that this space-time division is relativized, and it had obviously lots of other consequences as well. Even this obviously divide between energy and matter. In other words, energy, matter and interactions also gets relativized in some sense. And I think that the general lesson I want to extract from this is that we can have a beautifully well-constructed theory, but it can be encumbered in our minds with a metaphysics, which it somehow persists in part because we haven't been sufficiently critical. And we've imported notions from other areas of experience, like sound waves and water waves, which all need a medium after all. And so we import ideas from other aspects of experience, perhaps because we haven't been sufficient, and we're not sufficiently conscious of those importations. And then it takes a very deliberate additional creative act, in the case of Einstein, to recognize that there's a particular mathematical feature of this theory that we don't really know what it means. We don't know how significant it is, and actually show that that is the key point, which leads to a new way of thinking, a new interpretation of the theory. So I would say that the situation that we face with quantum theory is just a severe, like an extreme case of this, where there's really nothing in the theory that you look at and you can just read off the metaphysics from with any degree of reliability. So where we would like to be with respect to quantum theory is something like this. I believe that we simply want this kind of coherence from the metaphysical level all the way to the specific physical theories. But what we have, of course, is the quantum mathematical framework here, just the finite dimensional von Neumann axioms, but there are many other pieces to this as well, such as the symmetrization postulate, the spin statistics theorem, the classical quantum correspondence rules, the Dirac equation, the Proctor equation. I mean, there are many other pieces that we need and use, but this is really the heart of it. And what we would like is to be able to, well, what we're trying to do in a sense is go from here to here, but it's extremely difficult to do that. And traditionally, the main approaches that we've tried are concepts like complementarity and entanglement, coined by the founders of quantum theory, and then no-go theorems like the Bell theorem, the Koch-and-Specker theorem, and then there are others in recent years. And these have the benefit of being very, very precise, very targeted. They target like a specific concept like non-locality or contextuality, but they're rather negative in the sense they tell us how we can't think about quantum theory relative to classical thinking, classical physics, but they don't tell us positively how we should think about it. So for example, Bell's theorem is typically called theorem of non-locality, but that doesn't mean that quantum theory is non-local. It could be non-separable. It could be, there are different ways of understanding this, right? But these theorems don't tell us how we should or could think about quantum theory productively. And then, of course, there are traditional interpretations, many worlds, de Broglie, Bohm, and so on. The main difficulty with these is that they're pretty much doing this kind of what we saw with Maxwell's equations pre-Einstein, is they're looking at the formalism. So they're trying to extract features from the formalism that seem to be understandable and interpretable, but they're ignoring most of the formalism. So for example, let something like many worlds would sort of, for the things like the complex structure, the Hilbert space structure, the unitary transformations, the tensor product rule, all of this is kind of in the background. It's not interpreted explicitly. So what they are really is, I would say, schematic interpretations or interpretations of a schematic quantum theory or a generalized kind of probabilistic theory rather than of quantum theory itself. And so, in other words, they're leaving money on the table, right? From an interpretational point of view, they're not interpreting an awful lot of that mathematical structure, but it is that mathematical structure, after all, which is responsible for the fantastic predictions of quantum theory over a course of 100 years. So the challenge then is really, how do we go beyond this, right? How do we combine the rigor of the no-go theorems, but at the same time generate a grand narrative, which is so attractive from the traditional interpretations of quantum theory? Can we combine both of these aspects together? And so this is really what I see as the promise behind the quantum reconstruction program. And the basic idea is, in a picture, is something like this, that rather than trying to figure out what the quantum conception is directly, let's find physical principles that are articulated in an operational framework very much patterned after Einstein's reconstruction of Lorentz transformations. Let's formulate physical principles and then show how we can derive mathematically the quantum mathematical framework. And then this is what we would call a reconstruction of quantum theory. And then once we have that, right, if we can get that, then we have successfully distilled the full mathematical content of quantum theory in a set of physical principles, which we hope will be a lot more philosophically digestible than trying to chew glass, so trying to actually directly interpret the mathematical formalism of quantum theory. And so this program of reconstruction is something that I believe, I would say, is it only really got started in any serious way around 2000. Lucian Hardy's reconstruction of the finite dimensional von Neumann axioms is one of the earliest and still widely cited. When I worked on reconstruction in my PhD thesis, this program didn't even have a name. Well, I didn't even know what to call it. I call it information theoretic approach to quantum theory. That was my PhD thesis. And when I published my work, it was still at that point, you were kind of arguing for this idea of reconstruction. Now I would say there are about a dozen reconstructions out there of the finite dimensional quantum formalism. There are very, very few in comparison of the classical quantum correspondence rules, the symmetrization postulate for handling identical particles, and of the spin statistics theorem. I don't know any recent reconstructive work. And this program of interpretation is, again, the idea of interpreting quantum theory through reconstruction. This has really hardly got off the ground. That there are very, very few people. I would find it difficult to think of a single person I could point to who's actually really seriously doing this. I think what's happened is that the number of people working on reconstruction is relatively small anyway, and most of them have then gone on to do other work in physics. And so in my case, it's only after doing reconstruction perhaps for something of the order of 15 years that I decided to go out of my comfort zone and engage with philosophers in a serious way. And Harald is one of those, I've been engaging with. And so it's been a very humbling experience to learn the relevant philosophy and somehow make sense of the physical principles. So just to make this point really clear, just to summarize, the idea of this program of interpreting quantum theory is that we first of all formulate physical principles which, when naturally mathematized, lead to the quantum formalism. That's reconstruction. And again, just to emphasize quantum formalism, but I mean by that the abstract von Neumann formalism, the quantum symmetrization algorithm, correspondence rules, etc. Because we need all of this whenever we apply quantum theory. We never apply just the von Neumann axioms. We have to employ a whole clutch of algorithms whenever we apply quantum theory to any physical system of interest. And then the second step is, the philosophical step is to develop a conception of reality which makes sense of these physical principles, easier said than done. But the idea is the output of that should be a conception, a metaphysically clear conception that we can put alongside the classical one, like a one-to-one correspondence, right? We can actually say, this part is preserved, this part is not, and this is why it's not metaphysically. We oughtn't ideally be pointing back to physical phenomena to justify the change. It should hang together, I would hope, metaphysically. Now, to substantiate these very general statements that I'm making, I want to look at a special case, which I've been engaged with now for several years, which is the nature of identical quantum particles. And there are really 4 questions that I've been looking at, and I probably won't get to all of them, but I want to talk about them nonetheless, briefly. The first is, we have a bunch of rules for handling identical particles. The symmetrization postulate is the best known part of that, but there are other parts to it, to the algorithms that we used. And so we want to understand what is the physical origin of those. So that's where reconstruction comes into play. And the second is asking, but why do we need these rules at all? Is there some deeper reason, except the bare phenomena that we see, like with the helium atom, the spectrum? Of course, we need these rules, but is there a reason other than these kind of very complex phenomena that we can point to, which would give us an understanding of why is it that when we have identical particles in classical mechanics, we don't need any special rules? When we've got non-identical particles in quantum theory, for example, in a hydrogen atom, we don't need any special rules. So why is it that when we have identical particles in a helium atom, all of a sudden we need special rules? And then this is the metaphysical part of the question, of the project, you could say, which is what kind of objects are identical quantum particles? So Dirac put out this idea of indistinguishability a very long time ago, almost 100 years ago. And in the philosophy of physics literature, there's a great deal of discussion that's been going on for 30 or 40 years about the nature of identical quantum particles. Are they persistent or not? Are they re-identifiable or not? And if so, and if they're not one of those, how should we conceptualize them? And then this is you could say a physics consequence of all of this, which is to ask about entanglement of identical particles. It turns out that although entanglement is well understood, and we know all about identicality, when you put these two ideas together mathematically, you get some absurd conclusions almost immediately. And it's an active area. There's a lot of papers published in the last 10 years on this topic of how do you talk about entanglement of identical particles in a sensible way? And it has experimental consequences as well, which I'll get to at the end. So very interestingly, when it comes to the rules for handling identical particles, there's not even widespread agreement about what those rules actually are. So this is actually a case where quite different than the von Neumann axioms, where there's almost universal agreement that, yeah, they make sense, they're consistent within their own scope of application. And second, so this actually already kind of foils, I would say, a lot of interpretative efforts, right? If you try to interpret the rules and you actually disagree what the rules are, then all of a sudden you have a recipe for disagreement and confusion. The second problem is that discussions of these rules is invariably mixed up with empirically warranted rules, right? The rules to some degree are obviously empirically warranted, but people such as Dirac made justificatory statements and interpretative claims, which are typically conflated with those rules. And we see that in the textbooks, for example, people talk about indistinguishable particles right off the bat, which is exactly what Dirac said, but that's already an interpretative and justificatory statement. It's not empirically warranted, and I'll get to that in a moment. So to start off with, I have to say, what are the rules? What are the rules that we actually apply? If I've got a box of helium gas and we look at the spectrum of the helium, and we want to create now models, a model of the helium atom, how do we do that? Step by step, what we would do is create, first of all, a foil model. In other words, a quantum model which makes no special allowance for identicality. So we just take a helium atom, we model it classically, we write down the classical Hamiltonian, we use classical quantum correspondence rules to get the corresponding quantum Hamiltonian, we plug that into the abstract Schrödinger equation, and we get a multi-particle equation for the two electrons. We solve that equation, we get the energy eigenstates. So at that point, I've not said anything special because these electrons are identical. The second step.
When you say they're identical.
Right, sorry, I should say, perhaps flag this right away. That we're talking about the intrinsic properties of the same. So two particles with the same mass charge.
So the spins are opposite in the
right, I should have said spin as well. So the same mass charge and spin, yeah. So
the spins will be different, right?
Yes, but even so, they're identical. So we have to make a distinction between intrinsic and extrinsic properties. So identical, we mean that we've made that cut already between intrinsic and extrinsic, or static and dynamic properties. And so two particles are identical if the intrinsic properties are the same.
Saunders would say they're weakly discernible.
I disagree, and I will explain. Yeah. The literature. Yeah, the literature is enormously diverse, and so there are all kinds of opinions out there. So the idea of what I'm trying to do here is approach this whole question in a much more systematic way, starting by reconstruction. So here I'm just kind of reviewing the existing state of knowledge prior to reconstruction. And then we employ what I call the no overlap rule, which says, look, if I have two electrons in separate hydrogen atoms, their wave functions basically don't overlap. And so I don't need to go any further. At this point, I can just stop, and I have a viable model of 2 electrons in separate hydrogen atoms. But if I have a helium atom, and I talk about the reduced states, of each electron, we will find that they overlap significantly. And then the no overlap rule says, well, in that case, you have to go to step 3. And step 3 is really the heart of this algorithm. It says that we have to symmetrize the wave function with the sign determined by the spin statistics theorem. So this is the symmetrization or anti-symmetrization of a wave function. And we have to also impose a constraint on the kind of measurement operators. We have to restrict ourselves to operators that are symmetric in the indices. So this is the algorithm that, it's in the textbook. This is what anyone who's being trained to use quantum theory will do, whether they're necessarily aware of it or not. These are the steps that they will go through. Now, this is a recipe that works extremely well, but there are some serious issues that arise if you scrutinize it. So, for example, if you construct a quantum model, a Fourier model at this stage, the index, let's say we take a product state like this. For example, think of an electron in the 1s state, an electron in the 2s state. Let's say we take a product state like that. At this point, indices 1 and 2 clearly refer to electron 1 and electron 2. And that interpretation is inherited from the classical model, where the electrons can be labeled and because they are persistent over time. And at this stage, certainly we have to interpret the indices in the same way, because otherwise we couldn't meaningfully talk about the reduced state of particle 1 or particle 2. And what almost universally happens is that interpretation is carried through to step 3 as well. So if we have now a symmetrized state like this, indices 1 and 2 are again sought to refer to particle 1 and particle 2. However, because of the symmetric operator constraint, it's actually impossible. I mean, we're disallowed from writing down measurement operators that refer to particle 1 or particle 2. So there's now a conflict between an interpretation that we almost unconsciously accept because that's what we're assuming here and here. There's a conflict between that and what we can actually measure. Right, so we have reason to doubt the interpretation. And it's only literally over the last decade or so that a few people in philosophy of physics, people like Adam Colton and I think Thomas Bigay, Dennis Deeks is the name I was thinking of, who actually suggest that this interpretation is wrong, that we can't interpret the indices as particle labels. The trouble is that we do refer to them here as particle labels. So something changes at this point, and then the question is why? Why is that?
Could I ask you if this is part of your you're assuming Higgs is right here. This is why. Yeah?
Well, you could say that's exactly what's going on metaphysically. Yeah. Yes. I mean, so we're assuming that the particles persist as individuals over time, and so yes. So even as we run through this algorithm, there's a consistent interpretation. The second problem, which I want to point to, is this thing here, right? So if I have 2 electrons in 2 separate hydrogen atoms, theoretically, the reduced states do overlap. They may overlap very, very little, but they do overlap. If I have 2 electrons in separate galaxies in 2 separate hydrogen atoms, their wave functions also overlap. You may say they don't overlap very much, but there's a finite overlap, right? So it's only in the mathematical idealized limit where you have 2 electrons in 2 infinite potential wells when their wave functions don't overlap. So this has a heuristic quality about it. And for that reason, you might say, well, let's drop it perhaps entirely. But that's not an option either because of this guy, right? So if you drop this assumption and if you have 2 electrons and 2 separate hydrogen atoms, and now you symmetrize the wave function, even then, then this step here says, well, now you can't, there's no meaning to the idea of where is electron 1. You can't do it. And you may think that maybe that's not a problem, but think about particles in a bubble chamber. We certainly label consistently a particle throughout a track. So we definitely sometimes do need to say that this is the electron I'm tracking through the chamber. So the point I want to make about the quantum symmetrization algorithm is that really it's a recipe-like thing. It's a recipe. It's not like a pristine piece of formalism like the von Neumann axioms. I want to now briefly talk about this issue of the mixing up of formalism, or you could say the recipe I've just mentioned, with additional language, which has a justificatory or interpretative nature. So the notion of indistinguishability has become bound up with these rules ever since 1926. And we see that here in Dirac's 1930 monograph, right at the beginning of his discussion of the mathematical formalism, right? So he puts this right at the beginning. He says, if a system in atomic physics contains a number of particles of the same kind, the particles are absolutely indistinguishable from one another. No observable change is made when any two of them are interchanged. This circumstance gives rise to some of the curious phenomena in quantum mechanics having no analog in the classical theory. So he's actually already bringing in an interpretation of the seed concept from which he's claiming all of this formalism follows, the idea of indistinguishability. The absolutely is to contrast it with Gibbs' relative indistinguishability relative to an imperfect observer. And when he talks about interchanging two particles, there's an implicit metaphysics there that the particles are persistent but not re-identifiable. So we can swap two things, but you can't tell. So there's an awful lot in this statement. And these ideas are propagated almost to the present day in our quantum theory textbooks. In every quantum theory textbook I've seen, that the same sort of language is used. And in almost all the literature in philosophy of physics, these same ideas propagate through. But I think this is a recipe for confusion because already we're mixing together the formalism and a rather elaborate story behind it. So as I say here, it's a partial justification, and it's also, some people say that's an implication of the symmetric operator constraint, but it presupposes that we interpret the labels, the indices 1 and 2 as particle labels. So it's already a lot in that. So now I want to switch gears and say, okay, so given this is our situation, we have a recipe that works. It's historically mixed up with a lot of justificatory and interpretative statements. We've not made a lot of headway in making sense of the nature of identical particles, which is, after all, the real goal here. So this is an excellent job for reconstruction, right? So we want to do reconstruction in a sense in the kind of Einsteinian style where we start off with an operational framework that's very austere, very minimalistic, and we focus on the data, and then we bring in additional assumptions very, very consciously to make sense of that data, to structure the data. So the first thing here to notice is that if you look at something like a bubble chamber image, we talk about there being tracks. This is common language, where we talk about the tracks, and the geometry of the tracks is how we gain information about the particles. But these tracks are made of bubbles. We never actually see these particles explicitly. This is all we see. It's like when we look in the sky, this is Harald's wonderful example, we see vapor trails, but we don't just see vapor trails, we also see airplanes leaving those vapor trails. But in a cloud chamber, we only see the vapor trail, right? So the very idea that there is a particle over and beyond the trail is a mental construction. that we can only indirectly justify. So the idea of reconstruction is something like this, that imagine I've got two electrons in two separate traps, electromagnetic traps, and we've characterized them, we've measured the mass and charge and spin of these. And now we bring those boxes together, we bring those traps together, we open the partition between them, and now we've got, we would say, two particles in the same trap. That would be our natural language description. But now let's deliberately focus on what we really know, which is like the data, right? So imagine that I have this, throughout this box, a means of conducting reasonably precise position measurements. So the raw data would simply be that I have two flashes at one time and two flashes at another time. And it's the fact that I see two flashes at each time that justifies this idea that there are two particles there. And now the normal story that we tell about this data is to say that there are two persistent entities in the box. So in the intervening time, unseen by us, either this transition must have occurred or this transition must have occurred. We're not making any speculation about path, because we're well educated in quantum theory. We know that the notion of a trajectory is a bad idea. So we just say, look, that is the transition, that one of those transitions must have occurred. But if we're being now mindful of our assumptions, our implicit assumptions, we realize we've already made a very significant metaphysical assumption here. That is to say, when we have two electrons in separate traps, we are assuming that the electrons are persistent, at least in that experimental context. We need to make that assumption in order to even measure mass to charge ratio, for example. But when we have two particles, two electrons in a box, in a single trap, now all of a sudden that assumption is something that we should be wary of. And we realize then that there's another possibility, another way of constituting or like framing the data, which is to say that there's a single object which yields, when interrogated, two flashes at each time. Now here we're departing from everyday intuitions. We normally assume that an object exists in space precisely where it appears, right? So we make this movement from appearance to existence. But what we're actually saying here is that although these are the appearances, we can conceive of a more abstract object, which isn't located here or here. This is a more abstract kind of object, right? So this would be this in mereology an extended simple, or a topologically disconnected extended simple. So metaphysicians who talk about objects in a more abstract sense, at least entertain the possibility, the logical possibility of objects of that nature. And so what we're really saying now is that these two flashes are not appearances of two separate objects. They jointly constitute the appearance, the momentary appearance of a single object. And so now the question is, well, can we do anything with this, right? So we could just say we have two different ways of thinking, two different ways of explaining the data, as it were, on the basis of the concept of a persistent object. But what do we do with it? You may think, well, you're kind of stuck, because ordinarily to make a predictive model, you have to make a commitment to one or the other. But what we want to do now is to try to synthesize these incompatible models in some way. So we certainly do this in everyday life, scientific practice. We have continuum and discrete models of water, for example. We haven't any problem with that. But the question is then, how do we synthesize quantitatively these two different models? And this can be done, and it gives rise to the quantum symmetrization algorithm, or a systematic form of that. So I just want to briefly lead you through this so that it doesn't appear to be completely out of the blue. So the idea is that we can describe each of these models in the Feynman formalism, associating an amplitude, a complex number, with each of these transitions, and likewise the transition in the non-persistence model. And we can then posit a connection between these amplitudes. So the intuition here is something like this. We know from ordinary application of quantum theory that we can calculate these amplitudes by classical quantum correspondence, but we have no direct way to calculate this. So we have space to inject a new physical idea, a new physical postulate, and this is what at some point I call the operational indistinguishability postulate. I don't think it's a good name, but I'm sticking with it. So this is the basic mathematical form of the postulate where h is some unknown function to be determined. And then this generalizes, so it turns out you need to consider flash, flash, flash as well. And here there's an analogous function g. And now you can derive a series of functional equations by deriving the same amplitude in different ways. For example, here we can compute the transition of this amplitude by mentally breaking this up into two successive experiments. And we're multiplying using the Feynman product rule. And also we can directly look at the whole experiment and then work out the amplitudes of each of these using, again, the regular Feynman rules. And then finally, we combine them together using the g function that was posited. So we've got two different expressions, mathematical expressions for the same transition amplitude, and for consistency, they must agree. And there are two other functional equations of that kind. And then finally, we have an isolation condition which reflects, again, operational reality. I can do an experiment on a hydrogen atom in my lab. You can do it in yours. There must be circumstances when that's acceptable, that we can do those experiments without worrying about what the other is doing. And so what we can do is to impose this condition that I can work out transition amplitude u, you can do a transition amplitude v, we work out the transition probabilities, we multiply them together because they're supposed to be statistically independent. We can calculate the amplitude of the transition using the h function and work out the probability of that transition, and they must agree. So this is a requirement coming from the operational level. And when we solve these function equations, we get the Feynman form of the symmetrization postulate. And very nicely and rather importantly, this does generalize to any number of particles. So those of you who happen to know the literature on this know that there's something called paraparticles that were proposed, which arise when you have more than two particles. But here we only get what's empirically needed. So we have now, in essence, reconstructed the quantum symmetrization algorithm. I now changed the name to procedure. Essentially, the idea is you use the persistence model to construct the initial model, quantum model of the system. And then you apply the operational indistinguishability postulate to construct the synthetic model that formally integrates these two different ways of constituting the data. And that's it. There's really only two steps. But if you want, you can apply the isolation condition, see if that applies to your experiment. And if it does, for example, if it's two hydrogen atoms in two separate labs, the isolation condition applies, and then the persistence model alone is sufficient. So briefly then, what do we learn about? This is the reconstruction part. So what do we learn? What can we extract from this? Well, classically, we have what I've already mentioned, this basic notion of point particles that persist with a distinction between static and dynamic properties, and we've got non-disturbing exact measurements. And in classical physics, what that means is that we can re-identify a point particle by successive measurements, and we look for proximity. That's our fundamental means of re-identification. But once we've re-identified, we can make measurements of the intrinsic properties, let's say mass. And if the particles have different mass, we can re-identify by simply measuring the intrinsic properties afterwards. Right? That's enough. We don't have to track. But if the particles are identical, this is again just classical physics, classical thinking, it's no problem. We can simply re-identify by tracking them through the arena of interaction. So no special accommodation is needed for identical particles in classical physics for this reason, classical mechanics at least. But what happens with quantum theory? So we're just adopting as primitives now the idea of physical system, measurement, and interaction. The critical idea I want to take out of quantum theory is that measurement is an active process. So what this means is that when we design experiments, interaction and measurement have to be kept apart, at least to some degree. And this is the key point. This is the key difference I want to rely upon. So the idea is that if you've got now a quantum system with two, let's say a muon and an electron, we can re-identify simply by measuring the intrinsic properties before and afterwards. But if the particles are identical, if you have two electrons and they come in and we would say collide and then separate, then we can't track the electrons all the way through the arena of interaction. Right? We can do a rough tracking, but not sufficient to be able to re-identify them. And so what we see here is the following, that we can't, in principle, always re-identify two electrons when they're interacting. And as a result, if we still believe that electrons are persistent under all circumstances, we'll see that we're actually making a metaphysical assumption that we have no empirical basis for any longer. Right? So the way I phrase this is the notion of individual persistence loses empirical cover. So this is where atomism essentially gets in trouble. And what's going on then in the reconstruction from this point of view is that by having these dual models and synthesizing them, we can relativize the concept of individual persistence to an experimental context, so that there are some contexts when we can think of the particles as persistent, but in other cases, like the helium atom, we can't. So very briefly, I know I'm a little over, sorry. So just very briefly, what kind of objects are identical particles? So one way of thinking is that these different models are incompatible models, but we can synthesize them. And so they're complementary models in the sense of Bohr. So this is I propose a new form of complementarity, but now to do with identical particles. And then from a more metaphysical point of view, I would say that now it's the microscopic detection events that are ontologically primary. So why do I say that? Well, because the two models that we have make different claims, conflicting claims about the nature of the microscopical objects. So it's actually the detection events that now are primary. Right, so particle is merely one way to thread detection events through time. But we, of course, have a macroscopic frame of objects. So this connects with Paavo's talk. But everything I've said presupposes that we have some macroscopic frame of objects that enables space-time coordination of events. I'll say this and then I will conclude that this is the idea of potential parts versus actual parts that I mentioned at the beginning. So the idea of this sort of distinction between these doctrines is if I have a compound body and I divide and I get two parts, can I say that those parts existed prior to the division? If you say yes, then, and if you say that's true unconditionally, then that would be the atomistic, that would be, sorry, the actual parts doctrine. The potential, so in other words, according to the actual parts doctrine, the parts already existed and the process of division was merely a separation of those pre-existing parts. The doctrine of potential parts would say, well no, the act of division is a co-creative process. It co-creates the parts, and potentially also the whole ceases to exist as a result of the process of division. And the doctrine of potential parts goes all the way back to Aristotle and was preserved by scholastics. So what would I say about identical particles? I believe that the appropriate metaphysical frame is to think of them as potential parts in the following sense, that the persistence model captures the parts, and the non-persistence model captures this idea of the whole. And the mathematical synthesis between them shows that this notion of whole is not a vacuous linguistic notion. It really has real power. So you could see the causal role played by the whole on the parts very precisely through the symmetrization postulate, which I posit to basically interpret to be a bridge between these two models. So we have the situation where that something like the helium atom is, as it were, kind of a microcosm. Yes, it feels the universal laws that apply to everything, but it also locally, as it were, modifies those laws through the symmetrization postulate. Okay, thanks. I'll stop here.
So to me, there's something lurking in the background, in addition to this idea of Higgsing, which is the principle of identity with indiscernibles of Leibniz. So if you look, for example, Simon Saunders will bring this into
Right.
in this context. So if you try to see how your idea of how to deal with this interacts with that principle?
Yeah, I mean, Simon's work really is presupposing what I was the assumption I was questioning, that the indices refer to persistent particles. So that the sort of this is the assumption that's built into the work. And so the idea is that, okay, if they are persistent, then is there any sense in which you can talk about in other words, how can you get out of this problem of absolute, the complete inability to re-identify? So really that his work is predicated already on this assumption that I'm already questioning.
Yeah, I thought he was trying to show the absurdity of doing that, so we could talk about that more.
Okay. Okay. All right. Thank you.
Thank you for your very stimulating talk. Is it correct somehow to say that you interpret complementarity as referring to the ontological level? So it is not an epistemological notion. It's somehow you suppose that the ontology itself, the basic ontology, is complementary in this sense. Would it be?
I would say that basically the bigger kind of, I suppose, claim behind this is that we need to move away from metaphysics as a claim about reality as it really is in a black and white sense. So the idea is that we have two different, if you like, metaphysical claims about the microphysical reality, and then we are facing a situation where neither of those by itself is sufficient. And then we have to do this magical sort of mathematical synthesis of these models to get a viable predictive model. So the idea is that we perhaps need to consider a metaphysics which doesn't sort of nail down the nature of the microphysical objects themselves. So if you want certainty, we can talk about events, detection events and detectors. So that's the level of, if you like, classical certainty or classical definiteness. But at the deeper level of making assertions about the microphysical reality, there we have to accept a fundamental and irreducible sort of ambiguity.
Yeah, I'm just wondering about the assumptions that we make in the classical case, and in fact, that it is an active assumption that we do have re-identifiable particles also in the classic case. as opposed to thinking of these apparent particle trajectory as sort of single object. We have a classical field.
Yes.
Got value in here, value in here, zero everywhere else, and when the two particles sort of collide or intersect, it's a classical field with value 2m. And again, the particles, the paths are just potential, and we are making a theoretical assumption that, we're making we're seeing this sort of pattern that seems very natural. One thing is going through here, one thing is going through there, but there's underdetermination. There might be physics that we don't know that makes these two particles bounce off each other, and then the trajectories are like this, or indeed they are merely potential paths, and it's just a classical field which has these funny delta configurations, and so I think they are hidden assumptions, even in the classical case.
Yeah, one thing I didn't distinguish between is like the context of discovery and the sort of later interpretation. So in other words, you could say that the classical framework presupposes the individual persistent entities. But of course, you could say, 100 years later, you could go look back at classical mechanics and think of it like a cellular automata or something like this, where there's simply one object and all the particles. There's sort of a material monist picture where all of what we think of as separate objects are really just manifestations or modes of a single physical thing, right? The universe, the material universe. So you could reinterpret classical mechanics in that way. But I would say that, first of all, it's either or, right? So they've got no particular reason to choose one or the other. And also, the sort of the monistic perspective has never really had any bite, so to speak. There's been no physical reason to adopt it. But I think that quantum theory is different in both respects. First, you can't have you can't have the persistence model with individually persistent particles or the non-persistence model. You need a synthesis of both. You can't get away with either. You need the persistence model to understand what's going on in a cloud chamber. You need the non-persistence model as well if you want to explain the helium atom spectrum. So I think that with quantum theory, you're in a kind of unprecedented situation where we need to kind of consider both.
Just like the ability to interpenetrate is an assumption in that sense. So that makes things consistent. So it's all idea of how we can have interaction when particles that have to coincide. Yeah. So that makes sure there's a coherent way of thinking, as you said. Which is important to keep in mind.
Yeah, that's true. Yeah.
I was wondering if you had a look at the Hongo-Mandel effect in this context, because you really have two particles coming.
Yeah.
They become indistinct.
This is actually the next slide.
Okay.
Right. So I'll just show it to you because I've got the experiment and I can
this
actually.
Seems like an experimental verification of your symmetrization postulate.
Yeah. Okay. So I'm just going to skip to the diagram here. Yeah, so there are wonderful experiments like in quantum optics where you can do, I mean, this is amazing, where you can take, let's say a photon coming, this is a beam splitter, a photon coming in like this, and one coming in like this. And so these are sort of representing the classically possible trajectories. And then you put detectors here, polarization measurements, essentially, and you post-select for the case that you get one here and one here. And it's been known in the literature for some time, but Bose and Home, in a paper in Physical Review Letters in 2002, showed that there would be Bell-violating correlations between those measurements. And that's pretty incredible if you think about it, because this beam splitter acts unitarily on individual photons, right? This is a linear optical element. So there's no interaction between these photons as far as we know, right, based on this beam splitter, but theoretically, you get a Bell violation. And, just those of you who know about quantum field theory, you can, in a quantum optics language, write out how this initial state evolves, and you get the spin entangled state from here. Oh, wait, yeah, there's a delta. Anyway, forgive the mathematics. So the point is that here we're seeing some really amazing stuff, and I didn't get into this, but the question this raises, now this is a physics question, is that are we seeing some sort of entanglement generation here as a result of this simple experiment coming from identicality? But the way of thinking that comes from my way of understanding identical particles is that the correlations we're seeing here are a manifestation of the holistic object. Right, this is not entanglement we're producing. This is a different effect. We're seeing Bell violations not because of entanglement. This is because of the holistic object from the non-persistence model. So this is a completely different way of thinking about the formalism.
Just to say that
Yeah.
there's games of switching between representations. Here, voting angles, there's spectral angles, completely two different things. So
Yeah.
That makes the difference.
Okay.
Here, then here. Phrase my hands here.
This.
I'll take it. It's a challenging job. You said there's a difference. You said like there's a difference between the thinking about the system as a whole object and thinking about it in terms of entanglement.
Yes.
To me, that's the same thing. Can you comment on that?
Yes. Sorry about. So entanglement is at the level of I would say it's at the level of properties. So I have two objects that normally the way of conceptualizing entanglement would be to say, look, you've got two objects, one exists here, one exists here, and yet there's some property that they have.
My thinking, way of thinking about it is that it's the same form.
Yes.
One object.
Yes, but I think that the point is, yes, I know you could frame it in that way, but
I just want to say,
yes,
it is possible to think of
you could. I would say that you could think of non-local correlations in that way, but entanglement, the very concept presupposes that I've got an object here. I've got two separate objects. I have to have separability in order to even interpret the formalism in that way. Yeah, well, that question is, well,
I know that people do this,
right.
and I don't believe that it's right.
Okay, well, let's talk. Yeah, that would be great.
Sorry.
Yeah, thanks. So I have a question about the reconstruction program in general, and finding these principles, because I'm very interested in principles of quantum gravity. So I'm wondering, finding these principles, does it help us to potentially combine it with those of GR and find some more fundamental theory? Because every time I've looked at this, I can't find any sort of aspirations towards that. Do you think it's a possibility? Is it an aim, or could it help?
Absolutely. I mean, reconstruction has a lot of different aims, and people who work on it realize it could be useful for many things. I mean, without the reconstruction of the Lorentz transformations by Einstein and the Minkowski formalism, and then writing Maxwell's equations in tensor form, it's difficult to see how GR would have come about, right? In other words, there's a kind of a creative trajectory towards new theories. I think with reconstruction, there's a similar hope. Absolutely. I mean, there are people who are working much more actively in that direction. I mean, Czeslaw Bruckner, Lucian Hardy, in their own way, are working towards those sorts of generalizations. So absolutely.
Okay, just a question of clarification. Do you need here a difference between ontology and epistemology? Because it seems to me that you cannot but assume that this particle persists in time unless you want them to be recreated each instant anew. But from the fact that you cannot identify them in time, you cannot assume that they don't persist.
Not sure I understand.
As a-
I agree that if we can't re-identify, let's say in certain contexts, then the assumption of persistences becomes questionable, and that's exactly.
What kind of notion of individuality are you working with? Say non-reductive, like a charity sort of individual?
Uh-huh. Yes. Yes.
Okay, so you're not Leibnizian in this sense.
I'm not sure if I'm going to give you the right answer. So maybe,
Well, we'll talk
I'm not
about
sure. Yes, let's do that.
Just a small comment about the Bose-Home
Yes.
experiment. It reminds me of yeah, Bort's reply to EPR, in which he has the arrangement to produce the EPR state. Yeah, you've got this suspended screen with two slits, and you get particles passing through. You measure the momentum of the slit, and you produce the EPR state. The definite difference in positions and definite total momentum. But also there you have to post-select, because you only get it if the two particles in fact pass through the two slits. If they bounce back or something like that, then you don't have entanglement. Is that analogous?
It's an interesting point. Yeah, I mean the post-selection is critical here. But in this particular arrangement, but as it turns out, you can kind of have a cascade of these beam splitters, and in the limit, when you have an infinite cascade, post-selection is not needed. So there is a disanalogy there. So I don't know whether it seems to be, these sorts of experiments that post-selection is needed for any finite experiment. But if you consider the limit of it in some suitably defined sense, post-selection is not needed. So I'm not sure.
Sorry, Philip, I'm going to contradict you there. For just the bunching you get at a standard beam splitter with two indistinguishable photons, one coming from each path, you don't need any post-selection. In that case, I mean, you can kind of see it there in your equation. If the Kronecker delta is 1, then it goes to creation operator C, plus creation operator D over root 2 on the vacuum. That is just, again, certainly in quantum information, we would call that an entangled state. Obviously, you could view it as a superposition where you have a specific spatial partition that you're using in the representation. But again, I feel like we would call it an entangled state, and you don't need to post-select for that. If it will always be, if you put two identical photons, one going one way, one going the other way, into a 50-50 beam splitter, it will either be you get two coming out one port or two coming out the other, always.
Right, but here the important thing is that we've got one up, one down, right? So we've got horizontal and vertical polarization.
In that case, you'd see no bunching whatsoever because they're distinguishable.
But that's my point.
Oh,
so
okay.
it's a different experiment.
Oh,
right? So
okay.
you can get 2, 0, 0, 2 or 1, 1.
Yeah.
And the 1, 1 is what we post-select for in this sort of experiment.
Okay.
And it produces something quite different and spell violating. And that's the extraordinary thing.
Okay. I think that might be a difference from what I was.
Yes.
Sorry.
Yeah, no, that's fine.
I was going to point out that normally when you do Bell inequality violation, post-selection is a bad thing, because you would post-select and you can create false violations. I've written papers on this.
Right.
There's been quite some controversy on it. But in this case, the post-selection is local and parameter independent. So in this case, you actually do get a true violation of Bell inequality from this kind of setup. So the post-selection is there, but it's shall we say, not so detrimental as you might think.
Yeah, I think the post-selection here is innocent, and as I said, it can be essentially removed.
The thing is that you post-select the information that you have locally at each
Yes,
site.
exactly.
I'd like to add to the confusion of post-selection by saying that, in fact, if you can post-select in a quantum computer, then you have incredible power. So technically, post-PQP equals PP, which is an incredible complexity class, probabilistic polynomial time. So.
Okay. Thank you very much, Philip.
Thank you.
Thanks for this topic.